Here we have another population, and these are balls within a jar. So let's say that there are a total of 1 million such balls, and if you want to apply numerical results, let's say we assign numerical values to the red and the blue balls, and you say that a red ball has a value of 0 and a blue ball has a value of 1. Once we've assigned these values, now suppose the population had 30% reds and 70% blues, then the population mean would be 0.70, because each blue has a value of 1 and each red has a value of 0. Now you can assign different values. There's nothing special about 0 and 1. For example, you can assign 5 to reds and -1 to blues. So this would be an origin shift and also scaling. So for the remainder of the course, assume that the jar actually has 52% reds and 48% blues. That means 520,000 reds and 480,000 blues. So we have numerical values assigned to the data points of this population, the population being the balls in the jar. So we can now find the mean and standard deviation. For the mean, we will have 520,000 multiplied by the value which we have assigned to reds, which is 0, plus 480,000 into 1 being the value assigned to blues, divided by 1 million, or that will be 0.48. So remember we had the formula where it said sum of all data points for the mean. So when you're summing the data points, 520,000 times you'll find reds and you'll put a value of 0 for all of those, and 480,000 times you're going to find blues and you'll put a value of 1 for all of those. So the total that you'll get will be 480,000. You divide that by the size of the population, which is 1 million, and you get the mean to be 0.48. Now for standard deviation, again 420,000 times we are going to encounter a red ball which will have a value of 0. From that you subtract the mean, which is 0.48, and you square it, plus 480,000 times we are going to have a blue, and the deviation of the blue from the mean is 1 minus 0.48. You're going to square that, and then you're going to divide by the size of the population, which is 1 million, and you end up with 0.2496. So this is the variance. 0.2496 is the variance, and to find the standard deviation, you take the square root of the variance, which turns out to be 0.4996. Now in the real world, of course, many variables take an infinite number of values. For example, you have height. Now height can be, it's a continuous variable, so it can take many different values. For such variables, the distribution is a continuous distribution. So a particular value has a very small chance of occurring. So it has a very, very small probability tending to 0. For example, consider a height of exactly 5 feet 10 inches. Now you're unlikely to find any one person with a height of exactly 5 feet 10 inches. In a population, you may find people who are close to 5 feet 10 inches, but even those who are close may vary by at least a billionth or a trillionth or a billion trillionth of an inch. So for continuous distributions where the probability of having precisely a given height tends to 0, it becomes more meaningful to talk about a range of outcomes. Say for heights between the values 5 feet 9.5 inches to 5 feet 10.5 inches, rather than individual outcomes. So to plot a continuous distribution, we have density, that is amount for ranges that are for continuous distribution. So you have the density and then you take the range and you multiply the density by the range to get the probability. So it is not a particular value for data will have a probability tending to 0. So you'll have probability for a range. And to find what the probability for a range is, you look at the density for that range and you multiply it by the length of the range. So a very common and useful continuous distribution is a normal distribution, which has a density which looks like this. Now, what does this mean to have a density? Well, think of the example we had of a binomial distribution of reds and blues. There, if I told you, if you dip your hand into the jar, what is the probability you'll pick up a blue? And the answer was 48%. So for one number with a value equal to 1, the probability was 48%. But for continuous distributions, the probability of picking up one particular number, exactly that number, tends to 0. So we need ranges. So suppose I want to find what is the probability of a variable described by this normal distribution whose probability is given by this, lying in this range. So this is the range, and the probability of the variable lying in this range is the area under the graph for this range. So if the range is small, it will be approximately the length of the range multiplied by the average of the value of density at the ends of the range. So in the continuous distribution, the probability of one particular value occurring is 0. Instead, you have a finite probability for a range. Also note that the normal distribution is symmetric. What that means is that suppose you want to find the probability density 2 standard deviations above the mean. So let's say 2 standard deviations above the mean is this much. So you want to find this probability, or the density would be this, would be the same as 2 standard deviations below the mean. So this amount would be the density, this amount, and the probability that the variable will be greater will be given by this area, which will also be equal to this area. So this is the 2 sigma and this is minus 2 sigma. Examples of normal distribution from the real world. Well, suppose you have an apple orchard that produces 1,000,000 apples and puts them randomly into bags of 1,000 apples each, then the weights of the bags would be approximately normal. In fact, one of the most useful theorems in probability and statistics is the central limit theorem, which says that if you add up identical variables, then the sum tends to be normally distributed. So you add up random variables which are identically distributed, whatever the distribution may be, the sum would tend to a normal distribution as the sample grows larger, as you add a larger number of them. So here we have 1,000 apples in each bag, which is a sufficiently large number to give us the weight of the bag to be approximately normal. We are going to come back to the central limit theorem when we do inferential statistics. Values for a normal distribution are usually given in the form of cumulative tables. These tables are given in terms of the z variable. The z variable is defined as the variable value minus the mean for the variable divided by the standard deviation. For example, a variable that is one standard deviation above the mean will have a z equal to 1. So here we have a standard normal table which you cannot read, so you have to look at your slides. So in this table, we find that the value from minus infinity to 1 standard deviation, so that would be 1 standard deviation is over here, is written as 0.8413. So that equals 84.13%. So that tells us that starting from the value of the z variable to be minus infinity to the point where the value of the z variable is 1, the probability of the variable falling in this range is 84.13%. Now remember that the normal distribution is symmetric. So around nu, it is symmetric because nu has a z value equal to 0, because z is found by value of variable minus nu. So if the value of variable is nu, then it will be 0 divided by standard deviation, so still 0. So what we know therefore is that this area that is less than nu has a probability of half of the total, so the same probability as the remaining area for values above nu. And what is the total probability? Well, the total probability is 1. That's by definition the probability of the variable taking on some value has to be, if you take the all possible values, has to be equal to 1. Therefore, this probability is half. So from minus infinity to this point where its standard deviation is 1, if that is 84.13%, then what is this area? From z equal to 0 to z equal to 1, well then this area would be 84.13% minus the probability of the variable falling in this range, which is 50%. So this area will be 34.13%. So this is how you use the table to find the probability for the variable to fall in different ranges. Similarly, by symmetry, you would know that the probability of the variable falling between z equal to minus 1 to z equal to 0 also would equal 34.13%. So here we have an example of using normal distribution, we have the consumption of potatoes by the Irish to be normally distributed with a mean of 30 pounds a year and a standard deviation of 5 pounds. Now, strictly speaking, the consumption of any good cannot be exactly normally distributed, because the normal distribution allows for very high values or very low values at a very small probability. So ignoring those very small probabilities, we can say that approximately the consumption of a good can be normally distributed. Now, what we need to find is that we need to find the number of Irish who consume between 27 pounds and 31 pounds, given that the population of Ireland is 4 million. So essentially our strategy is to find the area under the curve from 27 pounds to 31 pounds, given that the mean is 30 pounds and the standard deviation is 5 pounds. And that area under the distribution curve is going to give us the probability, which we shall multiply by the population to get the number of Irish who consume in this range. So the deviation of 27 pounds from 30 pounds is 3 pounds. So the value, the z value, so let's say this is z low, will be 3 divided by 5 equal to 0.6. Now go to the standard table and look up the value for z equal to 0.6, and that value is 0.7257. So that is from minus infinity to z equal to 0.6. So from that you take out 50%, so you are left with 0.2257, that's 22.57%. So this is actually from z equal to 0 to z equal to positive 0.6. What we want is from z equal to 0 to z equal to negative 0.6, but by symmetry they are the same. So the probability of consumption falling between 30 pounds and 27 pounds is 0.2257, that's 22.57%. Similarly, from 30 pounds to 31 pounds, the z value is 0.20, so this you can say z high, or that is the value 31 exceeds the mean by 0.20 standard deviations. Now again go to the table and find what the value of probability for 0.20 is. Turns out to be 57.93%. From that, remove 50% and you get 0.0793, that's 7.93%. So there's a 7.93% probability that an Irish man or woman consumes between 30 pounds and 31 pounds per year. So, but you want the range from 27 pounds to 31 pounds. So you add these probabilities and you get the probability to be 0.3050. So 30.5% of the population consumes between 27 and 31 pounds. Well, the total number was 4 million. So you multiply 0.3050 by 4 million and you get your answer to be 1.22 million. So that is the number of Irish who consume between 27 pounds a year and 31 pounds a year. We now come to covariance and the correlation coefficient. So these are descriptive statistics that measure characteristics not of one variable like height or weight, but a pair of variables. The covariance is a measure of how together two variables move. For example, if one of the variables increases by 5%, then covariance is going to make a prediction about how much the other variable would have moved subject to some other errors. If the variables have a tendency to move in opposite directions, the covariance will be negative. So, for example, if you have two stocks and when the price of one goes up, the other has a tendency to go down, then the covariance between these two stocks will be negative. The formula for covariance is similar to the formula for variance, but instead of having the square deviations from the mean, we have the deviation of the first variable from the mean multiplied by the deviation of the second variable from the mean. So the first variable x from the mean of x multiplied by the second variable y from the mean of y, and we sum this for all the data points and then divide by the size. So you must have paired data. For each x there must be a corresponding y. So we have pairwise occurrences of the variables x and y. If you do not know the population means, then we can use the sample means xs and ys to form an estimate of the covariance. The correlation coefficient between two variables is the covariance between those variables normalized, that is scaled down by the standard deviation of those two variables. So this makes it dimensionless. And the correlation coefficient must lie in the range -1 to +1. A correlation coefficient of -1 means that the two variables are perfectly negatively correlated. Similarly, a correlation coefficient of +1 is perfect correlation. Here the two variables move in the same direction and you can exactly predict how much one variable is going to move from the movement of the other variable.